Everything you've ever seen, every star, every planet, every galaxy, every atom in your body, makes up less than 5% of the universe. The other 95%, we have absolutely no idea what it is. And it gets worse. This invisible stuff is literally ripping the universe apart right now. But here's what really should terrify you. We only discovered this 25 years ago. For all of human history, we thought we understood the universe. We were wrong about 95% of it. Today, I'm taking you on a deep dive into the greatest mystery in science. By the end of this video, you'll understand why some physicists think we're living in the dark ages of cosmology, and why the answers might rewrite everything we know about reality. Scientists call this missing stuff dark matter and dark energy. But let's be real. Those are just fancy names for we don't know. We can't see it. We can't touch it. We can't detect it directly with any instrument we've ever built. But we know it's there, because without it, galaxies would fly apart, stars wouldn't form, and you wouldn't exist. Think about that. We're made of the rare stuff, the weird 5%. Everything we've ever studied, every chemistry experiment, every physics equation, every Nobel Prize, is based on understanding, basically, a rounding error in cosmic terms. And here's the structure for the next 20 minutes. First, we'll unpack the dark matter mystery, how we found it, what it does, and why scientists are desperately hunting for it in underground labs right now. Then, we'll dive into dark energy, the force that's even more mysterious and is actively tearing the fabric of space apart. Finally, we'll explore the cutting-edge theories, the latest discoveries, and what this means for the ultimate fate of everything. Let's start with a puzzle that stumped scientists for decades. Our story begins in the 1970s with astronomer Vera Rubin. She was doing something that sounds simple, measuring how fast stars orbit around the centers of spiral galaxies. Now, this should follow basic physics. Think about our solar system. Mercury, close to the sun, zips around at 47 kilometers per second. Neptune, way out on the edge, crawls along at just 5 kilometers per second. Why? Gravity. The farther you are from the mass, the weaker the pull, the slower you move. Galaxies should work the same way. Stars near the bright galactic center should orbit fast. Stars at the dim outer edges should orbit slowly. But that's not what Vera Rubin found. She pointed her telescope at the Andromeda galaxy and measured the speeds of stars at different distances from the center. And what she saw made no sense. Stars at the outer edges were moving just as fast as stars near the center, sometimes even faster. This breaks the laws of physics as we know them. Imagine you're on a merry-go-round. Kids on the outer edge fly off if it spins too fast because there's not enough force holding them on. That's centrifugal force, overpowering the structure. Well, galaxies are spinning so fast at their edges that stars should be flung out into intergalactic space, like kids flying off a merry-go-round. But they're not. Something is holding them in, something we can't see. But here's where it gets crazy. Rubin and other astronomers measured galaxy after galaxy, hundreds of them. And they all showed the same impossible pattern. Every single spiral galaxy in the universe is rotating as if there's 5 to 6 times more mass than we can actually see. Either the laws of gravity stop working at galactic scales, which would overturn 300 years of physics, or there's a massive amount of invisible matter we've never detected. Scientists chose option 2. They called it dark matter. But calling it dark matter is like calling a mystery novel the book with pages. It's technically accurate, but tells you nothing about what's actually inside. Now you might be thinking, okay, maybe there's just dim matter out there. Dust clouds, dead stars, planets we can't see. Great theory. Scientists thought that too. So they started looking for machos, massive compact halo objects. Basically, dark stuff made of normal atoms that just doesn't shine. But when they calculated how many machos you'd need to explain galaxy rotation, the numbers didn't add up. There simply aren't enough dead stars and black holes to account for all the missing mass. Plus, we have another way to see dark matter. And this one's brilliant. It's called gravitational lensing. Einstein's theory of relativity tells us that mass bends space, and when space bends, light follows that curve. Imagine placing a heavy bowling ball on a trampoline. It creates a dip. Now, roll a marble past it. The marble's path curves around the bowling ball even though they never touch. Light does the same thing around massive objects. So when astronomers look at distant galaxies through galaxy clusters, the light from those background galaxies gets bent and distorted, like looking through a warped glass lens. And here's the kicker. When scientists map out how much the light is bending, they can calculate how much mass is doing the bending. And what they find is shocking. The visible matter, stars and gas, accounts for maybe 15% of the lensing. The other 85% is coming from something completely invisible. Pause and think about this. We can literally map where dark matter is by watching how it bends light, even though we can't see the dark matter itself. In 2006, astronomers observed something called the bullet cluster, two galaxy clusters that had collided and passed through each other. The normal matter, hot gas, got stuck in the middle, glowing in X-rays from the collision. But the gravitational lensing showed that most of the mass had passed straight through and was now on either side of the collision. Dark matter doesn't interact with normal matter except through gravity. It's like two ghosts passing through each other. This was the smoking gun. Dark matter isn't just missing light, it's a completely different type of matter that doesn't interact with light at all. So if dark matter isn't normal atoms, what is it? Scientists have three main candidates, and all of them sound like science fiction. Candidate number 1, WIMPs. WIMPs stand for weakly interacting massive particles. The idea is that dark matter is made of particles that have mass, so they create gravity. But they barely interact with normal matter. Trillions of them are passing through your body right now, through the Earth, through the sun. They're everywhere, but they're ghosts. Think of it like this. Imagine you're swimming in a pool, but there are also invisible fish swimming around you. You can't see them, you can't feel them, they don't disturb the water, but they're there, and if you had the right detector, you could prove it. That's what scientists are trying to do. Deep underground, sometimes more than a mile below the surface, researchers have built incredibly sensitive detectors. Why underground? To shield them from cosmic rays and radiation that would create false signals. These detectors are waiting for a single dark matter particle to collide with a xenon atom or a germanium nucleus. Just one collision would prove dark matter exists as particles. They've been running for decades, and they've found nothing. 0 confirmed detections. Either WIMPs don't exist, or they interact even more weakly than we thought, or we're looking for the wrong thing entirely. Candidate number 2, Axions. Axions are theoretical particles that are incredibly light, billions of times lighter than an electron. But what they lack in individual mass, they make up for in numbers. The theory is that space is filled with a sea of axions, so many that their combined mass adds up to all the dark matter we observe. It's like asking, what weighs more, a pound of feathers or a pound of lead? They weigh the same, but you need way more feathers. Axions are the feathers of dark matter. Scientists are building detectors that use powerful magnetic fields to try to convert axions into photons, particles of light we can detect. The Axion Dark Matter Experiment, or ADMX, has been searching since the 1990s. Some encouraging signals, but nothing confirmed yet. Candidate number 3, primordial black holes. Here's a wild idea. What if dark matter isn't exotic particles at all, but just a bunch of black holes left over from the early universe? These wouldn't be black holes from collapsed stars. They'd be primordial black holes that formed in the first fraction of a second, after the Big Bang from quantum fluctuations in density. Some could be tiny, smaller than an atom, but with the mass of a mountain. Others could be planet-sized. And here's the thing. They'd be virtually impossible to detect directly unless one happened to pass nearby. The James Webb Space Telescope and gravitational wave detectors like LIGO are looking for evidence of these primordial black holes right now. But here's the unsettling truth. After 50 years of searching, we still don't know what dark matter is. We know it's there, we can map it, we can calculate its effects, but we cannot touch it, see it, or catch it. It's like knowing someone is in your house because doors keep opening and closing, but you never see them. That's where we are with dark matter. Transition from dark matter to dark energy. Now, if dark matter is mysterious, dark energy is absolutely mind-bending. Dark matter at least makes sense intuitively. It's stuff that has gravity and holds things together. Dark energy does the opposite. It pushes things apart. It's anti-gravity on a cosmic scale, and it makes up 68% of everything that exists. Let me take you back to 1998, the year that changed cosmology forever. In the 1990s, two teams of astronomers were in a race. They were studying Type 1a, supernovas, exploding white dwarf stars. These supernovas are special because they're standard candles. They all explode with roughly the same brightness, so if you see one that looks dim, you know it's far away. If it looks bright, it's closer. By measuring the brightness and the redshift, how much the light has stretched due to the universe's expansion, you can calculate exactly how far away the supernova is and how fast the universe was expanding when that light was emitted. Both teams had the same goal: measure how much the universe's expansion was slowing down. See, everyone assumed gravity would be slowing the expansion. After the Big Bang, the universe exploded outward, but gravity from all the matter should be pulling everything back together, slowing it down. The question was, how much is it slowing? Will the universe eventually stop expanding and collapse back in a big crunch? Or will it expand forever, just getting slower and slower? So these teams measured dozens of distant supernovas, crunched the numbers, and prepared to announce how much the expansion had slowed. But when the results came in, there was silence. Then panic. The universe wasn't slowing down. It was speeding up. Galaxies weren't just moving apart. They were accelerating away from each other, faster and faster. It's like throwing a ball up, and instead of slowing down and falling back to Earth, it starts rocketing upward faster and faster, defying gravity. This shouldn't be possible. Unless there's a force we didn't know about, a force pushing space apart. They called it dark energy, and the scientists who discovered it won the Nobel Prize in 2011. But winning the Nobel Prize doesn't mean we understand it. We just know it's there. So what is dark energy? Honest answer: we have no idea. But we have some theories, and they range from elegant to absolutely bizarre. Theory number 1, the cosmological constant. This is Einstein's old idea. Back in 1917, Einstein added a term to his equations called the cosmological constant. It was a kind of anti-gravity that kept the universe static. At the time, Einstein thought the universe was eternal and unchanging, so he needed something to counteract gravity's pull. Then, in 1929, Edwin Hubble discovered the universe was expanding. Einstein called the cosmological constant his biggest blunder and removed it. But here's the twist: he might have been right all along. If dark energy is the cosmological constant, it means empty space itself has energy. Vacuum energy. Even in the emptiest regions of space, no matter, no particles, nothing, there's a tiny amount of energy inherent to the fabric of space itself. And as the universe expands and creates more space, there's more vacuum energy, which pushes space apart even faster. It's self-reinforcing. The crazy part? Quantum mechanics predicts vacuum energy should exist, but when physicists calculate how strong it should be, they get an answer that's 10 to the power of 120 times bigger than what we observe. That's a 1 with 120 zeros after it. It's the worst prediction in the history of physics. So either our quantum mechanics is catastrophically wrong, or something is canceling out almost all of the vacuum energy, and we don't know what. Theory number 2, quintessence. Maybe dark energy isn't constant. Maybe it's a dynamic field that changes over time, like an energy field permeating space. Scientists call this quintessence, literally the fifth element after earth, water, fire, and air. If quintessence is real, dark energy could get stronger or weaker over cosmic time. And that's terrifying for reasons I'll explain in a moment. Theory number 3, Modified gravity. Here's the radical option. Maybe Einstein was wrong. Maybe gravity doesn't work the way we think it does on cosmic scales. There's a theory called MOND, Modified Newtonian Dynamics, that says gravity behaves differently when it's extremely weak, like at the edges of galaxies. If that's true, maybe we don't need dark matter or dark energy. Maybe we just need new physics. But MOND has problems. It works for some galaxies but fails for others, and it can't explain gravitational lensing observations. So most physicists think MOND is wrong. But the fact that serious scientists are even considering it shows how desperate we are for answers. Now here's where this gets existential. Dark energy doesn't just affect the past. It determines the fate of everything. If dark energy is the cosmological constant and stays constant forever, the universe will keep expanding faster and faster. Galaxies will get farther apart. Eventually, every galaxy outside our local group will be so far away that their light will never reach us. Trillions of years from now, any civilization in the Milky Way will look up and see nothing. Just a few nearby galaxies and then endless darkness. They won't even know other galaxies exist. They'll think the universe is just their island of stars surrounded by infinite void. The cosmic microwave background, the afterglow of the Big Bang, will be redshifted into nothingness, completely undetectable. Future scientists won't be able to discover the Big Bang. They won't know the universe had a beginning. We're living in a cosmological golden age. We can see the universe's history. Our descendants might not be so lucky. But it gets worse. If dark energy isn't constant, if it's getting stronger, we face something called the Big Rip. Here's how it works. Right now, dark energy is weak enough that gravity holds galaxies, solar systems, and atoms together on local scales. But if dark energy increases, eventually it will overcome gravity in galaxy clusters. Clusters will be torn apart. Then galaxies will dissolve. Then solar systems. Then planets. Then molecules. Then atoms. Finally, even the quarks inside protons and neutrons will be ripped apart. Everything, every structure in the universe, will be shredded by runaway dark energy expansion. Some calculations suggest this could happen in 20 billion years. Others say 200 billion. The uncertainty is terrifying. Or there's a third option, the Big Crunch. If dark energy weakens or reverses, gravity could eventually win. The universe would stop expanding and start contracting. Galaxies would collide. The cosmic microwave background would shift to higher and higher energies. Eventually, everything would collapse back into an infinitely dense point. A reverse Big Bang. Some physicists speculate this could trigger another Big Bang, an eternal cycle of expansion and contraction. But that's pure speculation. The honest truth is, we don't know which fate awaits us because we don't understand dark energy. Now let's talk about what's happening right now in cosmology, because things are getting weird. The James Webb Space Telescope launched in 2021, and it's been sending back images that are breaking our models. Webb is looking at galaxies from when the universe was only 300 to 400 million years old. These should be small, messy proto-galaxies still forming, but instead, we're seeing massive, well-structured spiral galaxies. Galaxies that, according to our dark matter models, shouldn't exist yet. It's like finding a fully built skyscraper in a construction zone that started yesterday. But here's where it gets crazy. Some of these early galaxies are so massive and so well-formed that they're making scientists question whether our timeline for structure formation is completely wrong. If dark matter is real and works the way we think, galaxies should form gradually, over billions of years. These galaxies formed in a few 100 million years. Either we're missing something about dark matter, or we need to completely revise our understanding of the early universe. Then there's the Hubble tension. The Hubble constant tells us how fast the universe is expanding. It should be, well, constant, but when scientists measure it using the cosmic microwave background, light from the early universe, they get one number, 67 kilometers per second per megaparsec. When they measure it using nearby supernovas and Cepheid variable stars, they get a different number, 73. That's a 9% difference. It doesn't sound like much, but in cosmology, it's a crisis. These measurements should agree. They don't. Either our instruments are wrong, which seems unlikely because multiple independent teams get the same results, or the universe isn't expanding uniformly. Maybe dark energy is different in different regions of space, or maybe the cosmological constant isn't constant at all. Some physicists think this tension is the crack that will break cosmology wide open, the clue that leads us to new physics. You might be wondering, why does any of this matter? Dark matter and dark energy are billions of light years away. They don't affect daily life. But here's the thing. Understanding 95% of reality kind of matters. Every technology we use, GPS satellites, medical imaging, nuclear power, semiconductors, came from understanding fundamental physics. If we crack dark matter, we might discover new particles that revolutionize energy production. If we understand dark energy, we might unlock the secrets of space-time itself, maybe even learn to manipulate it. And philosophically, this is humbling. For thousands of years, humans thought we were the center of everything. Then, we discovered we're on a random planet orbiting an average star in a typical galaxy. Now we're discovering that even the stuff we're made of, atoms, protons, electrons, is the cosmic minority. We're the exception, not the rule. We live in a universe designed, for some reason, to hide most of itself from us. That's either terrifying or exhilarating, depending on your perspective. If your brain is melting right now, good. That means you're paying attention. Look, I spend dozens of hours researching these topics, diving into scientific papers, talking to physicists, and breaking down the most mind-bending concepts in cosmology, so you don't have to. If you want more deep dives like this, and I mean deep dives where we actually explore the cutting edge of science, not surface-level space facts, you need to subscribe right now. Hit that button, turn on notifications, because next week, I'm tackling something even stranger. What if we're living in a simulation, and dark matter is a rendering shortcut? Some physicists are dead serious about this idea, and the evidence is unsettling. Also, drop a comment right now and tell me, do you think we'll ever understand dark matter and dark energy, or are we fundamentally limited by the fact that we're made of the 5%? I read every single comment, and some of the best video ideas come from you. Thanks for sticking with me for 30 minutes. Seriously, that takes dedication, and I don't take your time for granted. I'll see you in the next one. Keep looking up.